Hello and welcome to this video about special right triangles. This is a follow-up to another video I made about them, and here we're going to take some time and understand the why and how they work. So first of all, let's talk about the core idea behind special right triangles. Really what they are, they're just shortcuts for the Pythagorean theorem. A squared plus b squared equals c squared. We're trying to avoid having to do that because we happen to notice some patterns. Now, in my other video, I went over what those patterns are, but I never really kind of stated how or why they work. So let's look at the first one, which is 30, 60, 90 right triangle. All right. Now, the origins of the 30, 60, 90 right triangle come from an equilateral triangle. So where all of these guys are equal in length. All right. And with that, each angle is 60 degrees. So 60, 60, and 60 degrees. Now, in order to get to the 30, 60, 90 right triangle, what you do is you take this equilateral triangle and you fold it in half. And when you fold it in half, what ends up happening is you make the bottom legs half as long as they were. So whatever the length of it was, it's now half of that. But the original one is still just as long as it was. And then what ends up happening is you still have the 160-degree angle here. You get a 90-degree angle there because you're folding it in half. And then the 60-degree angle gets cut in half and then becomes 30 degrees. And that happens right there. And so that's what the 30, 60, 90 right triangle comes from. Now, this 1/2, I mean, you can deal with it, but we don't really like it that much. So what we could do is we just times everything by 2, and then that's where we're getting this right triangle, or the 30, 60, 90 right triangle that looks more like this, where we have x, 2x, and then we can use the Pythagorean theorem to figure out what this one is right here. And so let's walk through that. So we have x squared plus, and then I'm going to use a different variable because we don't know what this is, so we'll just say it's y. So y squared has to equal 2x in parentheses squared. And so when we start bringing this all together, we end up getting x squared plus y squared is equal to 4x squared. Subtract x squared from both sides. And so continue my work over here. Y squared is equal to 3x squared. Take the square root of both sides. And so now y is going to equal square root of 3 and x, and then x squared. Now, this is a perfect square, so it's going to come on outside, and y is going to end up equaling x square root 3. And then that's why we have x root 3, root 3, right there. Now, one more thing I wanted to go over. I showed a little hack for if you're given a number on the longer leg. So if we had a triangle that looked like this and we were given this is 4, how can we figure out what this guy is? And I said that what we're going to do is you take whatever your side length is, you times it by root 3, and you divide it by 3. Let me try to explain where that comes from. But first, let me clean up this so I have some space to work. So how do we go from 4 to figuring out what the shorter leg is on our 30, 60, 90 right triangle? Well, keep in mind the pattern, oops, I put my pen back on. The pattern is, if we know what the shorter leg is, the longer leg is just x root 3. So to go from here to here, we're timesing by square root 3. Now, if I want to go the other way, what that means is I'm going to need to divide by square root 3. And so here's where we're getting into some fancier math with radicals. So what I'm going to do is I'm going to take my 4 and I'm going to divide it by the square root of 3. Now, I could potentially leave it like that, but in math, we don't like this because our denominator is an irrational number. The square root of 3 isn't a whole number. We want it to be something like just regular 3. So in order to make this look nicer, we times both sides, or we times both the top and bottom by root 3 over root 3. And then what ends up happening is these two just get multiplied together. They're two different sort of animals, if you will, 4 and square root 3. One's under a radical, the other one's not. And then root 3 times root 3 simply becomes 3. And so that's why that pattern is whatever we have here, we can times it by root 3 and divide it by root 3, and we're good to go. And again, that's sort of complicated, and you may or may not have enough understanding of radicals to kind of see how that works, but ultimately that's where it's coming from. Now, let's talk about the other triangle, which is the 45, 45, 90. So let me just clean this up really quickly. Get rid of that. Now again, with the 45, 45, 90, 45, 45, 90, again, it's still a shortcut for a squared plus b squared equals c squared. And so if you take a look at it, here we have an isosceles triangle. These are both 45 degrees, and then there's our right angle right there. Now, if we don't know what this is, x and x, we can, since it's isosceles, they're both equal to x, both legs are. Now we can use the Pythagorean theorem to see what the hypotenuse ought to be. And so that's where we would go, x squared plus x squared is equal to, and then we don't know what the other one is, so again, we'll just kind of call it y. So let's go y squared. And then we combine our like terms, so we'll have 2x squared is equal to y squared. And then just like we saw with the 30, 60, 90 right triangle, take the square root of both sides. We have the square root of 2x squared is equal to y, but since we have a perfect square in here, that can come on in, or that can come on outside, and so we'll have x square root 2 is equal to y. And so that's the pattern that we'll just take whatever our x value is, we times it by the square root of 2, and that's going to be your hypotenuse. And again, we're avoiding having to do that work. Regardless of what the numbers are, we can just plug it into this formula and put that number times the square root of 2. Now, likewise, I had an example in my other video where I said, hey, if this is a whole number, in order to go from here to here, what we're going to do is we put whatever our number is, times it by root 2, and divide by 2. We're going to see that it works very similar to the 30, 60, 90 right triangle. So let's just kind of see how, again, that would work. So draw the same sort of triangle. Let's pick a different number. Let's pick something like 5. All right, it'll be a little bit easier because it's not even, and you'll see why in a bit. And so we're trying to figure out what these are. Again, it's a 45, 45, 90 right triangle. It's isosceles, so the two legs are the same. We set it up to, so whoops, let me take my time here. X squared plus x squared is going to equal 5 squared. And so then that gives us 2x squared is equal to 25. Divide both sides by 2. And we have x squared is equal to 25 over 2. Take the square root of both sides. And then the thing is, you can take, when you take the square root of a fraction, you're taking the square root of the numerator and the denominator. So x is going to equal this 5 over the square root of 2. And as I showed earlier, we don't like having a radical in the denominator. So we rationalize it by multiplying by root 2 over root 2. So that way when we end up multiplying, or we can multiply these two root 2's together to get just regular old 2. And then the 5 and the square root 2 can't intermingle anymore, so that's as far as we go. And so that's what's happening with the Pythagorean theorem. But again, there's a sort of that shortcut, that hack, where we can just sort of take our hypotenuse, times it by root 2 over 2. And keep in mind, in a situation like this where it's even, and that's why I wanted to use 5 for the other example, is that these guys can simplify, and now we'll have 2 root 2. And sometimes it's harder to make that connection that 2 root 2 is going to become 4 when you go to the hypotenuse. But anyways, I just wanted to make a video to sort of explain the why and the how behind these special right triangles. Again, the core idea is that they are simply shortcuts for a squared plus b squared is equal to c squared. But now maybe you can kind of see where it came from and how it works, and hopefully that clarifies a few things.